Hello everyone, welcome to Python and Astronomy. So today we'll be doing some astronomy while sitting at home using a very high level language, although very easy one, Python. My name is Saurav. I'm currently doing my bachelor's in physics honors from Dal Singh College, University of Delhi. Currently in my final year, and I work a bit on Python and how we basically use Python for different aspects in physics, astrophysics, astronomy, or cosmology as a whole. As in today's era, we know that there's a lot of data that we have been receiving from all over the world. It might be through different detectors, some experimental techniques, or some telescopes. Let's say some radio telescopes or even optical telescopes. They gather a large amount of data, and then we use different techniques, different methods to basically understand how the data is behaving and what different astronomical and astrophysical aspects are going out there in the universe. We'll be just going with a brief introduction how basically we can try to use Python and what are the different resources that you can use while you're sitting at home and learn how you can try to be productive using these simple techniques, and you can learn it basically while you're sitting at home. We can just get started. So here I've opened some few links that I'll be providing in the description, where you can just go through and try to understand what exactly these links can provide you. So here there's one link which says Python for astronomers. In the starting, when you are actually just uh, wandering around like what you can actually try to do um, productive using Python, here is the first step that you can think it of is basically try to understand what exactly this programming language is, Python. This link actually provides a good description about Python, like how to go about it, what exactly is the format, and some tutorials as in are even provided in this particular package. Like here, first it goes through the introduction and motivation, like why are we using Python. So as it says, Practical Python for Astronomers is a series of hands-on workshops to explore the Python language and the powerful analysis tool it provides. Here they actually go out saying that workshop will immediately make use of full suite of plotting, analysis, and file reading tools. Now, this is actually a very essential part of astronomy when we are trying to understand the data that we have taken from optical and radio telescopes. So, as you can see, an image here. This is um, an image of some galaxy, let's say, and then you can see the different colors are there are different contours on this particular image, and they're having their own different properties. Now we need to understand what exactly this image is showing and trying to understand what depth it can tell us about this particular astrophysical object. So here they actually apply some coding using Python and then try to understand what exactly it is trying to do. You can actually go through this particular website and see and make yourself useful about going through this particular field and see how this is actually going to benefit you in the future or even whenever you are trying to use this particular thing. Although this particular website is not actually a very much straightforward use for those who want to go through the very basics of Python. For that, you can just log into, or you can just try to go um, the official website of Python and try to understand some basics before going into depth analysis in astronomy and different aspects. As if anyone of you, or if you are a bit much familiar with the programming language, you must know that there are certain libraries that we actually use in programming language that makes our lives very much easier. So here in Python, there are a few libraries which is actually essential beforehand, so that you have to install them and it basically makes your analysis very much easier. So, for example, the mostly used libraries in um, in scientific department that we use is NumPy, SciPy, and AstroPy, and different other libraries which we use. But the mostly used are these: NumPy, SciPy, IPython, or AstroPy. So these are actually some important libraries that you must have before you actually get started. So you can just try to make yourself useful and explore this particular website, and you can just go about there and see what exactly uh, these all topics are, and how you can try to use this and analyze some real data that's been taken from some optical telescope or any UV or gamma ray telescope, and try to analyze your data yourselves. Now, another aspect that you can see about in today's era is basically machine learning. Now, machine learning is actually one of the most important tools and one of the most important methods that have been used and is currently being used by astronomers and astrophysicists and different physicists as well, to understand the behavior and to see basically how our data is behaving, and to get a much more in-depth analysis of our data and that particular astronomical object. Now, if you're familiar, like, so normally machine learning is actually used, for example, in search for exoplanets. Now, as we know that there are many systems, as much same like solar systems, uh, which are out there in the galaxy, in the whole universe, situated around stars, and there are certain planets around them, surrounding it, just as same system or maybe similar system, just like our own solar system. Now, how do we actually search for those exoplanets? uh, you can see, maybe something like this, where there's a star and there's an exoplanet which is actually revolving around it, some planet revolving around it, and then how this particular planet is actually giving out a light curve that you normally see, and then you can try to understand how that light curve we are receiving and how the data is actually behaving as per uh, our analysis, and see if there is some exoplanet or not. Something like this in here. So there's a star and there's a planet which is revolving around it. Now, as the planet goes in our line of sight, we see that this continuous light curve that we are receiving here has a dip in it. Now, as it crosses our line of sight, it does go dip, and there's maximum or minimum, and then it reaches out as a planet completes its revolution, and then we see how this particular curve is behaving. Now, there's this GitHub repository by some person, and this is exoplanet ML, which is actually doing something, and which is having some data and has some codes and all the description about their how they're actually using it. You can just go through them and see how Python is basically being used to analyze this particular data set, and see something like this. Now, this is actually very much exciting, and you can actually try to do it on your own hands, and it is actually not that much difficult. It just requires some sort of um, numerical methods that you should know beforehand, and also a bit of astronomy, and then you are ready to go to analyze the real data. So this is one of the things that you can do using machine learning and Python at your home. It just requires that you are using correct resources, the data, and the correct programming. Now, another thing which is actually very much useful nowadays, as you can see, so one hot topic that's going in astrophysics is gravitational waves. Now, LIGO Collaboration has opened a website for people like us called Gravitational Wave Open Science Center. Now, this GWOSC, what it contains is basically tutorials on the workshops that it had uh, organized, that they have organized in earlier times, say in 2018, 2019, and they have uploaded some of the lectures, some courses that they have taken in previous times, and they've uploaded and opened it for public. So you can just go to the website and you can try to explore this particular thing, and then after that you can go to this quick view notebook. Now here they have, what they have done is basically they've uploaded some of the data from previous runs, from initial runs especially. As you can see, 150914, that's the very first detection, and then the related data sets, and then they have analyzed some data. So as you can see, while opening to one of the links, one of the notebooks, you can see that this binary black hole signals are like open data. So what they have done is basically they have first explained what exactly the programming is, and then they have given some important links which are actually important before you just go deep into the analysis, which requires a bit of understanding of signal processing as well. So you can just go to the websites and explore signal processing, and then basically go to this particular notebook which use some different libraries which they have used, which is H5P5 to basically handle data, then JSON, and then they have their own LIGO for reading, library for their own reading the data, which is feed LIGO, and then they have just imported the data, did some analysis, and this is something that you can see as a strain data they've collected for different frequencies. They've plotted in a very sophisticated manner, and then after particular time when you are deep down, they have plotted some spectrograms as well. Spectrogram is nothing but data which has been plotted as frequency versus time, like how the frequency is changing as the time is changing. So you can see how the spectrograms are plotted. So while doing all this stuff, you can even you'll be even learning a lot of physics stuff as well, because while doing programming you need to understand different techniques, and those different techniques will require at least some knowledge of physics as well. So as you can see, then also in this particular analysis they have plotted some chirp signal as well. This is a strain data, and then the already simulated data for gravitational wave template. They have already taken the template which was simulated by extremes, which says XXS, which stands for simulating extreme space times, and they have simulated the data. They have just imported it for different frequencies, for different strain data, and then they have tried to use this technique which is called match filtering technique, which is actually essential for gravitational wave data analysis, and to basically find where exactly our data is of the spiral of the black holes, or depending on whatever we have the sources from the very noisy data. And it is actually a Herculean task. As you can see, that it requires some massive sort of programming to find the signals. So a lot of noisy data, and still we are able to recover some of it using our template, and then see how we can actually remove some noise and get a beautiful curve, something like this. So this is one of the things that you can actually try to do by your own hands, and programming, the whole coding is actually written in a very sophisticated manner and in a very much easier way. So it's actually easier for anyone who is having some good knowledge of signal processing can actually understand this particular thing. Okay, so another thing is basically using Python for different things. So here's this website called AstroPython. You can explore this particular website, which is actually absolutely good for the beginners who just entered this particular field and want to explore what exactly can be done using Python and astronomy. So this particular website is amazing. You can just go to this particular website and explore different stuff. Now another thing that you can try to do, which I have done, is I have implemented GitHub page called SK Outreach, which was implemented for the Vigyan Samagam exhibition which happened, which is supposedly been going on since 2 months in Delhi now. So for the SK Outreach program, we created a GitHub web page for Pulsar hands-on session. So where we have uploaded some of the data, which is basically a pulsar data of a specific pulsar called Vela pulsar. So now this particular data sets, these are 1 second worth of each, and they have been uploaded. So what this particular repository is about is that there is some data and how to basically use Python to analyze this particular data sets and see how the pulses actually looks like, and how we can actually analyze some real data of radio data which was taken by from an Indian telescope called OT radio telescope, and analyze yourself to see how we can actually find the pulsar signals and also find the timings of it, which is basically the pulsar time. So this particular website, you can just go to it and see how I've created this particular thing, and see if you're having some trouble installing Python. So this actually goes through a very easier way if you're having Linux or Mac users, or if you are a Windows users as well. So you can just go to one of the notebooks section, and let's say I go to this particular notebook where I have plotted some of the signals already. So you can just go to it, and if you're having a bit of knowledge of signal processing and some data analysis, you can see how easy it can be. It's just that you need to know what commands being run. You will just understand that, and then you can do whatever you want to do with the data. So here first we have seen how the voltage and current characteristics are happening, because the data that we have been received are in the format of voltages. So the description of the data is given here, all about it. So you can just go about it and see how we have plotted the data. Firstly, the random data that we have been getting is basically what distribution it follows. So as we know from the central limit theorem, any random data that we have been taken in a very large amount should follow Gaussian distribution. This is the first thing that we have plotted, and then that's the power. Then we have this power spectra, how the power is changing. So this is the time domain, and how we have Fourier transformed it to the frequency domain. So you can see how the power is changing with respect to frequencies, which is the power spectra, and now the spectrogram or the dynamic spectra, how the frequency is changing with respect to time. So you can see these are the pulses, the slanted pulses, slanting due to a phenomena called dispersion, which means that the lower frequencies travel at lower speeds, not at lower speeds, but due to the interstellar medium they interact, and they lose their energy, and thus they travel at lower speeds due to their interstellar medium. And high energy high frequency waves reach us faster than the low frequency waves. So that's why we have seen lower frequency photons receiving us at a later time. Then we de-disperse the data and see how the signals, how the pulses are actually looking like, something like this. And you can just go, and this exercise that you can try to do is trying to find the time period of the pulsar using folding technique, and just trying to find what time this pulse is occurring, make a plot, and trying to find the time of the pulsar. So this is another thing that you can try to do is actually, which is called data analysis of radio data. Now another data analysis that you can the data analysis portion that you can do is basically the imaging portion. So whenever you have some data taken from a radio telescope, either you can try to analyze and see using different aspects, or another thing that you can do is basically try to image the particular source. So here I've tried to make my own code and try to see how we can actually try to image a particular file. So that requires several aspects. The first aspect is basically how do we sample our data, and also how the response of antenna is happening. So here I've plotted which is called a dirty beam, which is nothing but how the response is happening, the response the particular antennas are giving, which are in the form of point spread functions. There's just nothing but a point spread function plotted in 2 dimension. And then you can just go further, use different technique to see how You can visualize some simulated data, which is nothing but a Gaussian distribution, the point source as in. So this is another aspect of analysis of some radar data. Now, in this particular image, you can see that there's a very interesting thing happening. That there is a central object, a very compact object though, which is M87, the central part of the galaxy, and this is showing that how that central object, supposedly a very supermassive black hole, is curving space-time so much, and that the accretion disk around it is actually casting a shadow because the light from this particular portion is not able to escape out to infinity. Now, it required several simulations as well to see how this particular object may look like. Now, we can actually, Python is so powerful that we can actually try to simulate something like this in Python as well. So, here I've tried to simulate some data as well. So, you can see how easily and how um, easily you can actually try to simulate some data just by knowing some of the relativistic aspects which require understanding of general relativity and some of the programming languages. So this is a central object, supposedly a Schwarzschild black hole, and how the intensity is happening is basically there's a emission disk which is surrounded by this particular object, and how the intensity it is actually emitting off to an observer which is sitting at infinity, and how that particular observer is observing this particular object in the equatorial plane. Now you may just go further and try to uh, see how we can use interpolation methods and try to generate more and more data using less computation time and make our image much more clearer and much more better than this particular thing. Now this is a very simple model that I have used, is basically the inverse square relation. 1 by r square is how the intensity is changing with respect to r. Now in this image there is actually very realistic model where the accretion disk is there, where general relativistic magnetohydrodynamics is applied. That means there are a lot of physical astrophysical things is happening, and this is a relatively very much simpler model, but although it looks sort of similar, maybe not that much. So this is the intensity, how the intensity is changing as you are going towards the central part, how the intensity is changing, and suddenly there's a drop, which means that there is some object which is having very high redshift, which is not allowing the light to escape out from this particular object. And then how the intensity is suddenly increasing from here, this portion, and then how it's decreasing with respect to this radial distance. So these are different things that you can try to do for using Python and different aspects of it. You can just go through these websites. I'll just link you through all of it, and you'll be able to understand on your own. And also, if you are looking forward for some introductory part for learning more about Python, I'll even attach a simpler file through which you'll be able to learn very basic aspects of Python as well. So if you have any doubts or anything else, you can just ping me on my email, which is written here, or you can just go to my GitHub website, this github.com/relativist1, through which you can find this particular repository, and you can just explore this repository for more details. So I guess that will be it. Thank you so much for your time.